Hello and welcome to indexing. We usually have access only to a small part of the DB. So let's say there are many relations in our database and we are only interested in the instructors in the physics department. So that's a small part of all the data that we have. Um, when we are accessing such small parts of huge data, we need some additional structures to access data efficiently. So I have already told you that we prefer a sequential file organization where the records are sorted by key. What if the search includes some attribute which is other than the key attribute? In that case, your search now becomes very inefficient, isn't it? So in order to improve efficiency in such cases, we would like to create indexes of the attributes that are likely to be used in the search queries. So these are additional information which tell us where the records are. So think of them as pointers to records. So an index creates index can be created using many different ways. So for example, I can take the first 10 characters of the name column. So if I'm going to search by name, then I can take the first 10 characters of the name and then give a pointer, so that it's easier to access when the query contains names. Um, so the column prefixes for indexes can make the index file uh, much smaller, and that's one reason why I just chose to take the first 10 characters. In this case, this is just an example. I'm not saying that we always take the first 10 characters of name while creating an index, but I'm just showing you an example of how an index might look like. The whole point is that we want to speed up inserts as well. But how does this speed up insert? Well, this this can speed up the inserts as well, because you need to know when you are inserting where to go and save that file. Okay, so quickly let's brush through some basic concepts. We have an index file which consists of records called index entries. So these are index entries, and there are two parts. One is the search key and the other pointer. Now, search key is a set of attributes that are used to look up the records in a file. The pointer is used to access the data record. I'll show you an example, and this thing should be pretty clear there. There are two different kinds of indices: ordered indices and hash indices. You must already have got some idea what this might mean based on my file organization discussion in the last lecture, right? So ordered indices allow us to search keys that are stored in sorted order. In hashed indices, we search keys. The search keys are distributed uniformly across buckets using some hash function. So let's take a look at the ordered indices. So we have something called as a primary index. So in a sequentially ordered file, the index whose search key specifies the sequential order of the file. Right. So I have the search key for a table, and I also have some key on which the file is sorted, or the records are sorted in that file, right? So now if these are same, then I say I have a primary index. But the search key of the primary index is usually but not necessarily the primary key. Please do keep this in mind. Secondary index, an index whose search key specifies an order different from the sequential order of the file. We call such files as index sequential files when ordered sequential file has a primary index. Well, so let me just repeat. In this case of primary index, order of search keys is same as the order of data records. So here is an example. Hopefully this should make everything clear to you. So let's say I have an index file. So index file is made of two parts. So I have the key and I have a pointer. Now the each index record points to a bucket that contains pointers to all actual records with that particular search key value. So let's say I have so many search key values, and let's say I want to search by salary, but my file is not searched by salary. Okay, so since I want to search by salary, but my file is not ordered by salary. If salary were the key, then I call this as a secondary index, right? So what I'm trying to create here is a secondary index because the key values here are not used here in the file to store the records. Okay, so let's now take a look at how this works. So the first thing that we do is we have these buckets which are pointing to specific records over here. So let's see. So for example, 75,000 maps to 75,000 here, right? So for every value of 40,000 that you show over here, this block would map to those rows. So from 40,000, I can go to a block, and from that block, I can go to all records that have 40,000 as the salary. Yeah, so this is an example for establishing a search index. Now, why do I need this search index? Well, this search index helps me to quickly access the records with these search keys, which otherwise I would have to go through record by record and then compare with the search key. And I'll have to do this for all records because there's no guarantee from the order of this field, right? That 40,000 might not be the last value as well, for instance. We also have dense and sparse indexes. A dense index is where an index record appears for every search key value in the file. So if there is a one-to-one mapping, then I call this as a dense index. We'll look at a sparse index example also shortly. So here is another dense index where there are only these many departments, and for every department I have an index, and I have a pointer pointing to that particular index. Luckily here you will see that these records are already sorted by the department name, so I don't have to have multiple physics entries. So let's say there is one physics entry pointing to the first physics record, and from there I can follow pointer to go to the next record which is by default available, let's assume. So we could do this, and this is an example of a dense file index. Here is a sparse index example where I just selectively pick few IDs and use it for my index. This saves a lot of space. I don't have to allocate additional space as much as the number of keys are there, but this also means that I'll have to do a little more work while searching for that particular attribute. So let's say I have 10101. I'm lucky it is pointing directly to 10101. But what if I have a value between these two as my search? For example, 15151. So I'll come over here. 15151 is larger than 10101. So I'll go to the next record, but this 32343 is larger than 15151. So I'll go back to the previous record and then start going through each of these records to find 15151. So this is somewhere in a sweet spot between a dense index and having no index. Yeah. Okay. And one final idea is that sometimes we have a multi-level index in order to make the querying even faster. Okay, so this question should help you understand how all these things work together. Take a minute, pause this video and read this question before I start solving it. Okay, so let's break this question up and see what we have. Few things are given to you. It's told that the file organization is unspanned and the number of records is 16,384. Record size is 32 bytes and block size is 1024 bytes. So these are all given to you. So now I have to worry about an index record. So if I have to, so assume these are all our files that contain the actual records, and this is sequentially ordered. Um, Now I have to create a hierarchical index records, and we know index records has two parts, search key and pointer. So we have to decide how much, how wide the search key should be and what should be the size of pointer. So in this case, they turn out to be 6 bytes and 10 bytes, right? So the block pointer is 10 bytes, is already given to you, and the each record is 32 bytes long and its key field is of 6 bytes. That's also given to you. Since the key field is 6 byte, we are going to store the key field over here. So we that's why this is 6 byte as well. Okay, so we have some progress. So we are visualizing a multi-level index. We don't know how many levels we need yet, but it should look something like this, where we have the index entries here and the actual entries here. So let's start first with the easier things. How many records per block can we fit? So I know that the block size is 1024 and the record size is 32. So obviously I can fit 1024 over 32, that many blocks, that many records per block I can fit. How many data blocks do we need if we have that many records? So we already know that there are 16,384 records in total. So 16,384 over 32 would mean I need 512 blocks. Okay, so I have 512 blocks. Say let's say block 1, block 2, block 3, and so on till block 512. And each block has 32 byte records, record 1, record 2, record 3, and there are such 32 such records in each block. So this is what we have found out so far. So we now understand this side of the story. Now, how does the index block look like? So the index block would have the key and a pointer to point to specific records of our index. Okay, so now we know key is of 6 bytes and pointer is of 10 bytes. So that's 10 plus 6, 16 bytes altogether. Now, if there are 16 bytes altogether, and remember blocks are the same and they are properties of a file system, right? So in a file system, all blocks, irrespective of whether it's an index block or data block, the block size is same. So I have 1024 as the block size, 16 as the record size. So I'll have 64 records possible here. Okay, so my index records, there are 64 index records in each block, and 32 records in each data block. Okay, please keep this in mind. So I have key 1, key 2, key 3 up to key 64 and pointer 1, pointer 2 to point 64 in one index block, and then so on in other, and so many. I'll need so many index blocks. But how many exact index blocks do I need? So I know there are totally 16,384 records here. So 16,384 over 64. Why 64? Because 64 keys can fit in an index block. So I'll need 256 index blocks to map to all the keys. Okay, so now I have 256 blocks. So this is block 256. Let's say block 1, block 2 up to block 256, and pointer 1, pointer 2 up to pointer 16,384. So this is sufficient for me to point to all the records. Now this is good, but the problem is I still have 16,384 records over here, so it doesn't achieve a great deal of efficiency. So let's, sorry about that call. So let's just continue with the second part of can I improve the efficiency even further. So one way to improve the efficiency is to add another layer of an index block. So another layer again has 6 bytes of key and 10 bytes of pointer. So now I again can have 64 records over here, and now instead of 16,384 record, sorry, instead of double the records, I only have half the records here, right? That's 16,384 records only here. Now for 16,384 records over 64 would give me would need me to have 256 entries here, correct? So 256 entries can be put here in 4 such blocks. Does that make sense to you? So I can have 4 blocks. Altogether, this will have 256 entries because each one will contain 64 entries. This block is very similar in structure with this block. These are all index blocks. And this index block is going to um, point to these next level index. And from here, I can point to another level index and so on. Okay, so all I need is a block pointer. So for here, so this one would be the next one and this one would be the next one and so on. So if I do like this, so I can keep reducing the blocks here. Okay, so now if you go and read the question, the answer should be 256 and 4. In fact, the question asks, if the secondary index is built on the key field of the file and a multi-level index is used to store the secondary index, the number of first level and second level blocks in the multi-level index are respectively 256 and 4. So I have 4 and I have 256. Okay, I hope this is clear to you. In the next session, we'll take a look at B plus tree indexing, which is a very, very interesting way of indexing data. Thank you.